Welcome back, everyone. This is the fifth lecture on the cardiovascular system, and previously we learned how the heart actually beats. We looked at the electrical activity in one lecture, we looked at the mechanical activity in the previous lecture, so we now know how the heart works. And today we're going to learn about the blood that's actually leaving the heart and take a deeper look at how that volume of blood that's leaving the heart is regulated. So let's begin with our not really attendance questions. Pretty straightforward today. Define stroke volume. Define end diastolic volume. And at the arterial end of a capillary, what is the greatest force? So go ahead and try to answer those. And if we define stroke volume, that is the volume of blood leaving the heart, specifically leaving a ventricle in one beat. The volume of blood leaving the heart, specifically one ventricle in one beat. Next, define end diastolic volume. End diastolic volume, just what that word or what that phrase actually means is the volume at the end of diastole, specifically the volume of blood in a ventricle at the end of ventricular diastole. So when the ventricle is most relaxed, when it is at its most full, that is what end diastolic volume is. The volume of blood in a ventricle at the end of ventricular diastole. So this is just prior to ejection, just prior to ventricular systole. At the arterial end of a capillary, what is the greatest force? Well, remember there was hydrostatic pressure of the capillary, osmotic pressure of the capillary, and also hydrostatic pressure of the interstitium and osmotic pressure of the interstitium. And they were all, pulling or pushing on that liquid in the blood. And the greatest force at the arterial end was the hydrostatic pressure of the capillary. That was that pressure of the blood actually pushing its way out of the capillary. So, today we're going to talk about cardiac output regulation, and before we can do that, we need to define what cardiac output actually is. Cardiac output is going to sound very, very similar to stroke volume. Cardiac output is the volume of blood ejected from one ventricle in 1 minute. The volume of blood ejected from one ventricle in 1 minute. So you can kind of think about this as the volume of blood being moved by the heart in a minute. And the equation, and yes, you do need to know the equations that we talk about, cardiac output is equal to stroke volume times heart rate. Stroke volume, we've already said, is the volume of blood ejected from a ventricle in one beat. Heart rate is the number of beats in 1 minute. So if we multiply those together, the product is cardiac output, the volume of blood ejected from a ventricle in 1 minute. And at rest, the normal, average, healthy adult male has a cardiac output of about 5.25 liters per minute. 5.25 liters per minute. That's the volume of blood ejected from one ventricle in 1 minute. Now, this volume of blood isn't just, it just happens to be what the heart is moving. This is the volume of blood needed by the body while at rest in 1 minute. So if there is, more or less, then later on we're going to see that's going to kind of impact some things that go on in the body like blood pressure. So we need about 5.25 liters of blood to be moved per minute out of the heart. And if that's what we need, there has to be a way to regulate that. And we can regulate that. Our heart regulates the amount of blood leaving it. And we can regulate that one of two ways. Well, we can either regulate stroke volume by increasing it or decreasing it, or we can regulate heart rate by increasing it or decreasing it. So stroke volume times heart rate is cardiac output. If stroke volume goes up, then cardiac output goes up. Or if stroke volume goes down, cardiac output goes down. Same thing with heart rate. If your heart beats faster, more blood's going to leave the heart. Or if your heart beats slower, less blood is going to leave the heart. So cardiac output is the volume of blood leaving the heart in 1 minute. But we can increase that or decrease that by either changing the stroke volume or the heart rate. So let's look at heart rate regulation. Now, before we start talking about all the things that can affect heart rate, for all of the lectures that are left in this unit, we're going to be talking about things that are on the very last page of your outline. And if you go to the last page of your outline, you have this chart. So right now we're talking about cardiac output. Cardiac output, what was it? Stroke volume times heart rate. So we're going to start talking about things that can affect heart rate. And that's all of this numbered material underneath here. Next, we're going to talk about things that can regulate stroke volume. And that are these numbered items underneath here. So keep that handy because we're going to refer to it a lot over the next several lectures. So, heart rate regulation. Well, normal heart rate is 75 beats per minute. At rest, we've already learned that. And things that affect heart rate, either increasing it or decreasing it, are called chronotropic agents. Chronotropic agents are factors that either increase or decrease heart rate. Now, there are positive chronotropic agents that increase heart rate, and there are negative chronotropic agents that decrease heart rate. Positive chronotropic increase, negative chronotropic decrease. And let's go back and talk about the autonomic nervous system. We've kind of already talked about this when we were talking about the electrical activity of the heart. Well, the autonomic nervous system, the PNS and the SNS, these things can either increase or decrease the natural rate of the heart. We've already said that the parasympathetic nervous system, by way of the vagus nerve, can slow down that SA node. The sympathetic nervous system can increase the activity of the SA node. So the parasympathetic nervous system slows down the heart. The sympathetic nervous system speeds up the heart. PNS is a negative chronotropic agent. SNS is a positive chronotropic agent. Next, the Bainbridge reflex. Sometimes this is also called the atrial stretch reflex. Atrial stretch reflex. Now, real quick, I want to point out something that I noticed a lot of students kind of get mixed up in their head. I'm going to write two words here, and whoop, I thought I was. Atrial versus arterial. Those words sound very, very similar. They look a little bit similar. They are not the same thing. Atrial means pertaining to either the right or left atrium of the heart. Arterial means pertaining to arteries, the blood vessels that take blood away from the heart. So they are not the same. Going back over here to the Bainbridge reflex. The Bainbridge reflex is also called the atrial stretch reflex. Now, in lab, when we meet in person, is kind of demonstrated. Now, in an online class, we may not be meeting in person for lab. So we might not get a chance to demonstrate this for this particular class. But the Bainbridge reflex is a reflex in which when blood comes back to the heart faster than it was, the atria get stretched. We say when there is an increase in venous return. That's a word we're going to hear a lot. Venous return, the amount of blood coming back to the heart. When there is an increase in venous return, those atria are stretched. And when the atria are stretched, that activates the sympathetic nervous system. The sympathetic nervous system responds by increasing the heart rate. And we do that so that the blood that's now coming back to the heart faster is pushed away from the heart faster. If the blood sits there at the heart, we say if there is pooling of blood at the heart, then as it sits there and doesn't move as fast, it's at risk for clotting, and we don't want that. The Bainbridge reflex is a reflexive activity that prevents that from happening. The Bainbridge reflex, when there is an increase in venous return, the stretched atria activate the sympathetic nervous system to increase heart rate in order to prevent pooling of blood at the heart. Next, chemical regulation. Well, before we go to chemical regulation, let me go back to the Bainbridge reflex, because this is actually something that if you're in a class that does not have in-person lab, you can actually test the Bainbridge reflex kind of the same way we test it in lab. If you stand kind of upright for a little while, and you just stand there and you don't really move around a lot, let's just have you stand in place for 3 to 5 minutes. And once you've stood there for about 3 to 5 minutes, very, very quickly lie flat down on your back as fast as you can. And the moment you do, feel your heart and pay attention to what happens. Briefly, your heart rate will increase pretty significantly. And that's that Bainbridge reflex in action. All right, so going on to chemical regulation. Various chemicals can affect heart rate. For example, epinephrine. Well, epinephrine and norepinephrine, which work pretty similarly, these are the SNS, the sympathetic nervous system. How does the epinephrine work, or the norepinephrine? It increases the heart's permeability to calcium. And what we're going to see, positive chronotropic agents are almost always going to tie in to calcium. Calcium, when it gets into the heart faster, it allows the heart to depolarize faster. And if we depolarize faster, then we're going to get to the state of systole faster, because for every depolarization, we get one contraction, one systole. So epinephrine increases the heart permeability to calcium. Thyroxine. Thyroxine is a hormone from the thyroid. And thyroxine increases your cardiomyocytes' responsiveness to epinephrine. Well, we just saw epinephrine increases the heart's permeability to calcium. So if we make the heart more responsive to epinephrine, that will also make the heart more permeable to calcium. nicotine. Nicotine is the substance it's a stimulatory drug found in tobacco. And nicotine increases epinephrine and norepinephrine secretion. It basically activates your SNS. And we've already seen what epinephrine and norepinephrine can do, which kind of makes me laugh because without fail, everyone that I've ever spoken to that smokes says they smoke to relax. But nicotine is a stimulant. It does the exact opposite. Maybe it makes you feel like you're relaxed, but it does not relax you. It actually does exactly the opposite. Caffeine. Normally, epinephrine and norepinephrine are broken down, at a standard rate by your body, and once it's broken down, it can't have an effect any longer. Caffeine prolongs the effects of epinephrine and norepinephrine by delaying the breakdown of each of those, so they stay in your body active longer. Next, potassium, K+. Hyperkalemia means too much potassium. Hypokalemia means not enough potassium. Hyperkalemia, when there's more potassium, then more potassium diffuses in to the cell rather than out. So more potassium diffuses in, which inhibits repolarization. And if we inhibit repolarization, then we're going to slow down the heart rate. Hypokalemia, if there's not enough potassium, then more potassium is going to diffuse out of the cell. And this is going to hyperpolarize the cell. And if the cell is hyperpolarized, it makes it harder to reach threshold, which makes it harder to stimulate into a full action potential, also slowing down the heart rate. So both hyperkalemia and hypokalemia will slow the heart rate, but it does it two different ways. Now, before we talk about the next two things, I want to talk about potassium, because we've seen it a few times now over several lectures. Potassium, which is atomic symbol K, typically it's in its ionic form, K+. Now, earlier in the semester, we talked about vitamin K. Because they both have K in them, students tend to think that vitamin K is potassium. It is not. Please do not see vitamin K and think that it is potassium. It is something completely different. Potassium is its own thing. Vitamin K is its own thing. Next, calcium. We can have too much calcium, hypercalcemia, or we can have not enough calcium, hypocalcemia. Now, hypercalcemia will slow the heart rate down. Hypocalcemia will raise the heart rate. Now, this has to do with the movement of calcium across the membrane. But calcium, while it does have an effect on heart rate, it actually has much more of an effect on how hard the heart contracts, which is something we will talk about in the next lecture. But calcium does affect both the rate of a contraction, heart rate, and the strength of a contraction, which we'll see next class. So we've already said that cardiac output, stroke volume times heart rate. And now we've seen one way that we can regulate heart rate is by one way we can regulate cardiac output is by regulating heart rate. And the other way that we can regulate cardiac output is by regulating stroke volume. Stroke volume, remember, the volume of blood ejected from one ventricle in one beat. So if you look back now to your blood pressure chart that I showed a moment ago, I won't keep pulling it back up, but if you look on your blood pressure chart, underneath stroke volume, It says number 1, preload, number 2, contractility, and number 3, afterload. Those are the 3 ways to regulate stroke volume. Now, there are ways to regulate preload. There are ways to regulate contractility. So right now we're just looking at the 3 ways to regulate stroke volume, which is preload, contractility, and afterload. So stroke volume regulation regulated by preload. Well, preload is almost the exact same thing as end diastolic volume. They're not the same, but you can kind of think of them as the same. Preload is the stretch on the ventricles. And the more stretch there is on the ventricles, the more blood they can hold. So EDV is increased. When EDV goes up, preload goes up. You can think of it that way, or you can just think of them as the same thing, because for purposes of our class, they are so closely related, we could think of them as the same thing. When EDV goes up, preload goes up. When the volume of blood in the ventricle is increased, then the stretch on those ventricles is increased, the preload. Now, I want to jump down over venous return and next talk about Frank Starling before we talk about venous return. Frank Starling was something we probably talked about in Bio 137. The Frank Starling law of the heart, or the Frank Starling mechanism of muscle contraction, just says that the more a muscle is stretched, the harder it will contract. We talked about this in Bio 137, and we talked about this briefly, maybe when we were talking about the arterials. But we will talk about this several times this semester. Heart muscle is just muscle. It's a type of muscle. And any type of muscle, when you stretch it a little bit, it contracts harder. That's the Frank Starling law. When muscle is stretched a little bit, it contracts harder. So if EDV goes up, if preload goes up, if we've stretched the ventricles, then what are the ventricles going to do? They're going to contract harder. If there is more blood in the ventricle and the ventricle gets stretched, the ventricle responds by contracting harder. So let's think about what that means. If preload, I'll just abbreviate that PL, if preload goes up, which really means EDV went up, then the heart is going to contract harder. If the heart contracts harder, what happens? Stroke volume goes up. And if stroke volume goes up, what happens? Cardiac output goes up. If preload goes up, which means end diastolic volume goes up, that leads to an increase in stroke volume, which leads to an increase in cardiac output. Let's look at venous return. Venous return is one factor that can regulate stroke volume. The more blood that comes back to the heart, another way to say that is if there is an increase in venous return, then there will be more blood inside the heart. Another way to say that is EDV increases. When venous return increases, when more blood is coming back to the heart, that causes there to be more blood inside the heart. Increased venous return leads to increased EDV. And increased EDV, we just saw, increases stroke volume. And when stroke volume increases, that increases cardiac output. We will look at some other ways to regulate preload and venous return in a coming lecture. That was just to kind of dip our toes into it and see exactly what preload and stroke volume are. Another way to regulate stroke volume is contractility. Now, contractility can be a little bit tricky because at first it kind of sounds like Frank Starling. We've already said that Frank Starling says if I have an unstretched muscle and a slightly stretched muscle, then the slightly stretched muscle is going to contract harder. But contractility looks at something different. Let's say I have two muscle fibers that are stretched to the same degree. Well, Frank Starling says they will both contract with the same force. But let's say I put a little bit of calcium on the bottom fiber, but not on the top fiber, and now I stretch those two fibers to the same degree. The bottom one is going to contract harder, even though they are stretched the same. Contractility can be a little bit tricky to define, but we can say that contractility is the force of contraction of a muscle cell at a given degree of stretch. Contractility is the force of contraction of a muscle cell at a given degree of stretch. So it is unrelated to stretch. It doesn't have anything to do with the degree of stretch. It is just the force of contraction at some degree of stretch. And we can cause muscle to contract harder, or we can cause it to contract softer. So we can regulate contractility. And when we regulate contractility, the things that regulate contractility are called inotropic agents. Inotropic agents. There are positive inotropic agents that increase contractility, and negative inotropic agents that decrease contractility. And just like we saw with heart rate, practically everything that regulates contractility is doing so by regulating calcium. Calcium is a positive inotropic agent. We saw that it was also a positive chronotropic agent, but now we're going to talk about it as a positive inotropic agent. Think back to Bio 137 and the role of calcium in a muscle contraction. Calcium inside the muscle cell bound to troponin, which caused it to change shape, pulling tropomyosin out of the way, allowing cross bridges to form. And the more cross bridges that form, the more forceful the contraction would be. So calcium regulates the amount of cross bridges in a muscle cell, including cardiac muscle. And calcium, remember, also prolongs that plateau phase in the actual action potential. So calcium regulates contractility, and it does that as a positive inotropic agent. The last way to regulate stroke volume is by afterload. Afterload is defined a couple of ways. First way to define it is the pressure in the aorta just prior to ventricular ejection. Afterload is the pressure in the aorta just prior to ventricular ejection. So, depending on how current you are on American Heart Association stuff, when we hear about blood pressure, we hear 120/80. Nowadays, it's 120/60. 75. So either 80 or 75 is going to be the number that we're concerned with here. Keep that in mind. The other definition of afterload is the pressure that must be overcome before blood can be ejected from a ventricle. Afterload, the pressure that must be overcome prior to blood being ejected from a ventricle. So afterload resists blood ejecting from a ventricle. Let's see why that is. I'm going to very crudely just pretend that is a ventricle. And those little cross-looking things at the top, that's the valve, the semilunar valve. If this is the left ventricle, I'm going to call it the left ventricle. The left ventricle would have the aortic semilunar valve and the aorta leaving that ventricle. So the afterload is the pressure in the aorta prior to ventricular ejection. So when the ventricle is in diastole. Well, when we looked at our 120/75, the top number is the systolic pressure. The bottom number is the diastolic pressure. We'll talk about those at length next lecture. But really what that bottom number is, it is the pressure in the aorta during ventricular diastole. So if this ventricle that we've drawn down here is in diastole, what's the pressure in the aorta? Well, that's what we just said. It's 75 mmHg. Remember, pressure, always mmHg. So when this ventricle goes to contract, it's going to start to squeeze. And how hard does it have to squeeze before that aortic semilunar valve opens? Well, it has to squeeze, and as it squeezes, pressure inside the ventricle is going to increase. How high does it have to increase? What is it that causes a valve to open or close? Pressure, remember, has to be higher in the ventricle than it is in the aorta. So, if we were to just put a number on it, we would say the pressure in the left ventricle has to reach 76 mmHg, and then blood can be ejected. But let's look at what happens if the aorta has a pressure of 95 mmHg. So your diastolic pressure, that bottom number, is elevated. Another way to say that is there was increased afterload, because remember, that is afterload. Now, how hard does the ventricle have to contract? At which point will those aortic semilunar valves open? Well, now we have to squeeze until the pressure in the ventricle is 96. Or if this number were 100, then we would have to squeeze until we got to 101. So when that bottom number of your blood pressure is up, it means your ventricle has to work harder before blood is ejected. So the result is increased afterload leads to decreased stroke volume. Why? Well, because the heart has to squeeze for a longer period of time before those valves open. that leaves less time during that beat for blood to be pushed out of the ventricle. So as afterload increases, stroke volume decreases, which means cardiac output decreases. Now, that's really where we will stop for today, but I do want to talk about why that is bad for the heart. Well, one, it causes the heart to have to squeeze harder if we want to move the same amount of blood. Additionally, if we wanted to regulate cardiac output, the heart would have to beat faster to move the same amount of blood. If we wanted CO to stay the same, but stroke volume had been decreased, then to keep cardiac output the same, heart rate would have to increase. Causing the heart to squeeze harder or work faster puts stress on the heart, and that is why things like high blood pressure can be very, very bad for the heart. Okay, so that's where we will stop today, and our next lecture will start to talk about regulation of blood pressure, and that will take us through the end of this unit. Maybe there will be one more lecture, maybe there will be two more lectures, we'll just see how it goes, but we are very near the end of this unit now.